Another problem for you with the surprise at the end. So watch the end. The alloy titanium 6 aluminum 4 vanadium is used to make a cylindrical pressure vessel having closed ends with an inner diameter of 250 millimeters and a wall thickness of 2.5. Estimate the number of cycles to failure if the pressure vessel is cycled between 0, okay, I don't need this. I don't know why I wrote this. 0 and 15 MPa. Use the Smith-Watson-Topper equation, which I wrote over here. And we also have the answer, so we know we're doing the things correctly. Okay, so we have a cylindrical pressure vessel. So if you can imagine it, I'm not going to draw it, unfortunately, on the computer. But if you can imagine a cylindrical pressure vessel, we have closed ends with an inner diameter of 250. So let's write that down. D inner, and I'm going to convert everything to meters. In meters. The diameter inner is 250 e to the negative 3 because that was millimeters. So meters you divide by 1,000. We have a wall thickness in meters of 2.5 e to the negative 3. That's our wall thickness, right? Now, we want to estimate the number of cycles to failure. Now, in order to understand this problem, we need to understand that this is a complex state of stress. And in a complex state of stress, we use von Mises. And so I would go to my equation sheet right here, and I would say, what would I do? This one, multi-axial state of stress. I said complex. I don't know. I meant to say multi-axial. So here's what we do. We have to find the amplitude in all direction with the von Mises. It's sort of all directions. And then if principal stresses are not given, we can do this. The mean stress is given by the following formula. So I'm just going to take this so that we can reference it. And I'm going to put it right here. And here's what we're going to do. We're going to say we're going to have a hoop stress and a longitudinal stress. So let me say sigma. I'm imagining in my head. I'm sorry I can't draw on this, but in my head I'm imagining sigma x is the longitudinal direction, right? And this is going to be an MPa. I'm going to calculate it in MPa. First, let's write our pressure. So my pressure is 15 on the interior, right? So how do I calculate the longitudinal stress? Well, so to calculate the longitudinal stress, it's the pressure multiplied by the radius divided by the thickness. The inner radius divided by the thickness. However, I would write that down as one of the formulas. I think I wrote this at the very beginning of the course. So we have right here longitudinal stress, PR 2T. See, I forgot the 2. So using this formula, and then notice that the hoop stress is actually bigger by a factor of 2. So we'll remember that. So I can use this formula right here, and I can say that my sigma x, oh, and I have actually a picture to show you. If we go over, no, not here, here, say I have a cylindrical pressure vessel. Well, this is not really a pressure vessel, but imagine this was curved here, kind of a semi-sphere. Then we would have our x-axis this way, so this would be a longitudinal, and then tangential to it, we would have our hoop stress. And then we'd have our radial stress as well from the inside. And the inside is the largest part. That's a big hint. So now sigma x would be a longitudinal stress. And it would be P. So it would be our P multiplied by R. Oh, well, I haven't calculated R, so let's do that. My R, and it needs to be the inner radius. So I'm going to put that subscript there so that I remind myself that that's the inner radius. And since they gave us the diameter inner, we just have to divide that by 2. Was it inner? They usually give you the outside and the thickness, and then they want you to use those. But, okay, they gave us the inner. So we can say pressure in MPa times R in meters divided by 2 times the thickness in meters, so we're left with MPa. And this is it. Now we want to do a similar thing for hoop stress, but hoop stress is twice as much. So we can just say this one times 2. And then we want the radial stress. So sigma R subscript R, that's just going to be equal to minus the pressure because it's it's compressive, right? There's pressure inside. Okay? So once we have these, we're going to pay attention to this. It says the pressure vessel is cycled between 0 and 15 MPa. That means that our amplitude is half, is 15 minus 0 divided by 2. So that's 7.5. Or it's half for each of these. So in other words, my sigma 1a, my largest of these halves, is going to be this divided by 2. So let me just write this down here, and I'm going to say sigma 1a is going to be equal to this one divided by, nope, I don't want the corrections. This one divided by 2. And then we're going to say that we have 2 more. This is a 2, and this is a 3. The 3, so the 2 is going to be equal to this divided by 2, and the 3 is going to be equal to this divided by 2. Okay, now we have these values right here. So what we can do is find sigma A average. So sigma A average, I can't put the little hat on top, but I can't put it in the denominator here, in the subscript here. And so we're going to do 1 over the square root of 2 multiplied by the square root of, now we have to pay attention, open parentheses, we got sigma 1 minus sigma 2a, close that, squared, plus sigma 2a minus sigma 3, so sigma 2a minus sigma 3, close that, parentheses, squared, and then we add the last one, which is sigma 3a minus sigma 1, sigma 3a minus sigma 1, right? We close that, we square it again, and then we close that as well. We get a value. Now we have this value right here. Now what we're going to do, there's one thing that I have to specify. So here we have principal stresses because it's just a cylindrical pressure vessel. If we had some other forces like a torque, then we would have to find the forces in each component and then use this. So it would be a little bit different. But we're just focusing on this one right here. Now, how do we find the mean stress? Well, we have the maximum, so we have to find the mean of each and add them up together. So that would be, I'm going to copy this, paste it right here. So that would mean this divided by 2 plus this divided by 2 plus this divided by 2. Now, the reason why this is the mean stress, and it really looks similar to what we did for sigma 1a, sigma 2a, and sigma 3a, is because it's from the minimum is 0. Otherwise, it would be different. Like the amplitude and the mean are not necessarily the same. So we add them up, we get our mean just by adding them up, just like that. Okay, and now what we're going to do is we have our sigma m, we have our sigma a, it's going to be sigma m hat and sigma a hat, which is really not, I should call it bar rather than hat. Okay, bar. And we have sigma a bar, sigma m bar, which is what we're going to use. The sigma prime f, I still need to write that down, so I'll do that. Sigma prime f, that's given right here, 2030, and that's all we need. Okay, so this is the moment of truth. Drum rolls, please. Let's code this right here, n subscript f, and I didn't do the subscript. Okay, subscript right here. Now that's going to be 0.5 multiplied by the square root of sigma a. So let me close this square root and then divide it by this value right here. And close that as well. Now this part is 1 over b, and I don't have b. Okay, so we have to write b first. Let's do that. B is given right here, minus 0.104. Now we have our NF. And let's restart. We're going to have 1/2 multiplied by something, which is inside the parentheses, to the 1 over b. And close that. Now in here, I'm going to put a fraction. The denominator of the fraction is going to be this value right here. Now I just need to work on the numerator. It's going to be square root of something. Inside that square root, there's going to be the sigma max, which is another parentheses, multiplied by my sigma a. My sigma a is right here. And then inside that parentheses, I have sigma a again, sigma a bar, plus sigma m bar right here. Now I can press enter, and I see right here that we get the right value. So that's how you do the problem. Now, I told you that there was going to be a surprise, and I'm not going to disappoint. Here's a surprise. What if we wanted to estimate the max pressure allowed if we wanted 10,000 cycles till failure? And now you're thinking, oh my gosh, like we're going to have to do some algebra. It's going to get messy. Well, actually, there's a trick. So they are saying, what value does this have to be in order for this to turn out to be? Because remember, this is pulling from these cells, and these cells are pulling from these cells, and this cell is pulling from that cell, which is pulling from that cell. So it's all connected, right? And they're saying, what value does this have to be in order for this to be 100,000 cycles? If only there was a way to do that in Excel. Well, you're lucky, because someone thought of that. So we do a what-if analysis. If you go on the data in Excel, and then you click on this cell, and then you go into the what-if analysis, and you go to the goal seek, and then you say, I want this B23 cell to be 100,000 cycles, 100,000, by changing P. So we change the P cell, we press OK, and the result is that you need 15.79. Is that what they said? Yes. So only 5% more pressure decreases the life by 60%. That's why it's really important to understand fatigue. Okay, well, I hope this was fun and enjoyable and that you learned something. I think I did. And I will see you next time.